This is a continuation of 5-2, which are examples of mean, variance, standard deviation, and expectations of the discrete probability distribution. So I'm starting with example 5-5, which is an event that has theoretical probability. So we're rolling a die. The reason I'm able to find the mu and standard deviation is because all of my x's are numeric values. 1, 2, 3, 4, 5, 6. So this is what I'm rolling. I'm rolling either a 1 or a 5. The probability of each happening is 1/6. So this probability distribution is complete. It is discrete because you cannot get something between a 3 and a 4. And all of the probabilities are theoretical probabilities. So in order for me to find mu, I know that the formula is sum of all of the x's times its probability. So in order for me to find this mu, I'm going to take each of the x, 1, multiply by its probability, and plus the next x times its probability, plus the next x times its probability, plus the next x times its probability, 5, and 6. 1, 2, 3, 4, 5, 6, and the corresponding probabilities. Add everybody up, put this into your calculator. If anything, pause the video, and then you should be getting a 3.5. Now that's the average. It doesn't mean that you're going to be rolling a 3.5 on your turns, because that's not physically possible. What it means is if you roll 1,000 times or 1,000,000 times, on average, the number is 3.5. Now, in order for me to find standard deviation, I need to go through variance. The variance is, the formula is x squared times p of x, and then minus mu squared. So in order to find my variance, by the way, the mu and the sigma are used as global events because, or as population, because what we're looking for is we're doing the whole distribution. So mu and sigma are appropriate letters to use rather than this sample mean and a sample standard deviation. So going back to variance, sigma squared is given to me. So in order for me to find the variance, I need to get each of the x's square. So 1 squared is 1, and multiply by its probability, and adding up everybody, except it's not a 2, it's a 2 squared, which is a 4. Taking the next x, which is a 3, squaring it, it's a 9. The next is a 4, squaring it, that's a 16. The next one is 25. The last one is 6 squared, which is 36. And please do not forget to subtract the mu that you found in the previous example squared. Very carefully putting all of this into your calculator should get you 2.917 approximately. Now, in order for me to get the standard deviation, all I'm taking is the square root of the variance, and this will get you to 1.708 approximately. So what you have is you have a spread of 1.708, and you have a mean of 3.5. My next example is 5-11, so let me correct that, 5-11. And the distribution was actually given to you. It says a talk radio station has 4 telephone lines. If the host is unable to talk during a commercial or is talking to a person, the other callers are placed on hold. When all lines are in use, others who are trying to call in get a busy signal. The probability that 0, 1, 2, 3, or 4 people will get through is shown in a probability distribution. Find the variance and standard deviation for the distribution. So just kind of note, if you're asked a variance and standard deviation, you have to go through the mean. You can't just find the variance by itself. So what they gave us is the zero lines are busy, so there's nobody calling, all the way through. 4 people are trying to get through, so all 4 calls. Notice I have a 0.18, 0.34, 0.23, 0.21, 0.04. So all of these are probabilities. If you add all of them up, they will add up to a 1. So this is a discrete probability distribution. And also notice that if it's a frequency distribution, these are not theoretical probabilities, these are observed probabilities. So it's easier to figure this out, but the chances are that in this book it's given to you, because if we know that 20 people called out of 100, well, the probability of calling is 0.2. So this the distribution is given. If I'm looking for standard deviation, I have to go through all of the formulas. So let's start with the mu. The formula for the mu is taking the x, multiplying by its probability. So the first one is a 0, so it just goes away. 1 times 0.34. The next one is a 2 times 0.23. The next one is a 3, 0.21, and 4, 0.04. Putting this into a calculator very carefully, you should be getting 1.59. Let's move on. I need to find the variance. So I'll take each of the x's squared. So in this case, 0 squared is just 0. Times 0.18. Then I have 1 squared. 1 squared is 1. Times its probability. 2 squared is 4. Times its probability. Then I have 3 squared, which is a 9. Times its probability. And then I have a 4, which is squared 16 times its probability. And please don't forget to subtract the mu squared. Very carefully putting all of this into a calculator, you should be getting the variance equaling 1.262. Now if you need the standard deviation, you're going to take a square root of this number to get 1.123. Well, the standard deviation and the variance are very close because it's around 1. Square root of 1 is 1. So the next topic is expectations. And we know that the expectation is just a mean of the standard of the distribution. There's 2 examples that I want to show you. The first example is 5-12, which is a winning tickets. So expectation is good in looking at games. So lottery is one of the games that we're going to be talking about. And 5-12 talks about 1,000 tickets that are sold at $1 each. And you can win a smart television set valued at $750. We're looking for the expected value of the gain if you purchase 1 ticket. So, a couple of things to start with in order to start your expectation. You need to construct a probability distribution. So you need to figure out what your x's and what your probabilities are. Now, this is a game. This particular game has 2 outcomes. You will either win or you will lose. And what I'm actually going to look at first is not the x, but the probability of winning versus the probability of losing. Some of the materials in chapter 4 is now applicable because you are looking for probability of something happening. Now it's not going to be very intense like 4.3 or 4-3 or 4-4, but things out of 4-1 are really good to go. So there's 1,000 tickets sold. And $1 each. So if you purchase one ticket, you will lose $1. And if there is one television set worth $750 winning, only one out of those 1,000 tickets has the winning ticket. So the probability of winning is one out of 1,000. The probability of losing is the other 999. So those are my probabilities. Now the X is the dollar amount that you will actually win or you will actually lose. So let's start with the losing streak. So if I buy one ticket, I lose $1 and I will assign X to be -1. So this is where negative numbers make sense. You lose, the number is negative. You win, the number is positive. Now winning. If you win, you will win $750 worth of television. So $750 is your X, but you have to accommodate for the fact that you've already spent $1 on purchasing a ticket. So the actual X is 749. Be very careful. This is where you lose some numbers. So in order for me to find expectation, all I'm really doing is finding the mean. Let me label this as expectation. All you're doing is finding the mean, which is just 749 times 1 out of 1,000, and then plus a -1. So the math does come out. So what you're doing is you're putting all of this into a calculator. And if you do this very carefully, you're going to end up with a -0.25. Now, this expectation is from a standpoint of a person who's playing a game, because you are losing $1 or you're winning a TV set. So the question is this game fair? Well, a fair game would have an expectation of 0 because nobody wins, nobody loses. You're doing this for fun. A negative expectation, like you see in this case, means that each person is expected to lose 25 cents. So this is what my answer is. Each person is expected to lose 25 cents. Now, it doesn't actually mean that everybody pitches in a quarter. It means on average, a person who's conducting this game, for him, it doesn't matter who wins the television set. What he has collected $1,000, and then he goes and buys a TV set that's worth $750. So that's $250 that's in his pocket. And on average, that's about 25 cents per person. So for the person who conducts this game, this is a very good game. Let's take a look at another game. This is 5-13. 10 cards are selected from a deck of Uno cards. There's 2 cards numbered 0, 1 card numbered 2, 3 cards numbered 4, 2 cards numbered 8, and 2 cards numbered 9. If the cards are mixed up and one card is selected at random, find the expected value of the card. So, in order for me to construct a probability distribution, I need to assign a value to each X. So there's 2 cards. Zero, 1 card, 2, 3 cards, 4, 2 cards numbered 8 and 2 cards number 9. So these are my numbers. These are my X's. I can either get a 0, a 2, a 4, an 8, or a 9. Now altogether, I have 2 plus 1, 3, 3 plus 3, 6, and then 4 more, 10 cards. So the probability of getting a 0 is 2 out of 10. The probability of getting a 2 is 1 out of 10. The probability of getting a 4 is 3 out of 10. This is basic probability out of 4-1. The probability of getting an 8 is 2 out of 10, and the probability of 9 is 2 out of 10. Notice it does add up to a 1. Perfectly good answer. And in order for me to find the expected value, or really I'm doing is adding up all of the x's times its probability. So the expectation of this particular game is 0 times 2 over 10 plus 2 over 1 over 10. I'm running out of space on this one. Let me move this a little bit. Plus 4 out of 3 over 10 plus 8 out of 2 over 10 plus 9 out of 2 over 10. You put this very carefully into your calculator, you will get 4.8. What does it mean? Well, on average, the value of a card is 4.8. It makes a little bit more sense if you do this many times. The game has to be played many times in order to see the expectation. And it makes a little bit more sense if we put dollar amounts to it. So I hope these examples help with the homework. And this is the end of 5-2.